The next one is inverse Z transform. We have three methods to perform the inverse Z transform. The first one is inversion integral, second power series expansion, and the third one is partial fraction expansion. So the inverse of Z transform is the method to get the xn signal for a given xz signal by multiplying this xz with z with the power of -1. So the first method is inversion integral, which is a direct method of finding a sequence xn from its z transform xz, which equal to this equation that involves integration. So this method of inversion integral is not advisable to use since it's quite difficult. So the next method is power series expansion, which involve long division that has been performed on the closed loop expression. This one based on the recreating the power series expansion. For example, from example 3.16, if you are given this value of exact z divided by z minus 0.1, where z must be larger than 0.1, so we apply the series of expansion by doing the long divisions. So this one, we have this equation based on the long division of series expansion, and then from this equation for x naught we have equal to 1, okay, for x naught. And if we have x1 which is equal to 0.1, for x2 we have 0.2 squared, for x3 we have 0.1 cube. Therefore, we can conclude that for power series expansion, xk equal to 0.1 with the power of k uk. So the k is depend on this one in the bracket. The third method of inverse Z transform, which is advisable to use, is partial fraction expansion. This technique is valid if and only if the order of polynomials denominator n is greater than the order of polynomials m at the numerator. So n must be larger than m. Due to its relatively ease of use of the partial fraction expansion technique, this technique is much widely implemented to solve the inversion problems. However, care should be applied by examining the highest order of the numerator and numerator, where the order of denominator n must be larger than the order of numerator m. Then, based on this equation, after we apply the partial fraction expansion, this equation can be written in terms of composites of fraction as shown below, where this signal az is equal to a1 divided by the first pole z plus p1 plus a2 divided by, this is the second pole, plus a3 divided by this one, and so on.